Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. Welcome to online video lecture series. In this lecture, we will discuss about causality and polynomial criterion for physical realization. The previous lecture, we have seen the distortionless transmission through linear system. In that, we end up with the transfer function h of j omega equal to k into e power minus j omega t naught. Low-pass filter characteristics are something similar to this. At low-pass filter with cutoff frequency omega c. This is mod h of j omega, and similarly phase response will be minus j minus j omega t naught. Suppose if you want to calculate the impulse response in order to design ideal low-pass filter, calculate h of t. H of t is nothing but inverse Fourier transform of h of j omega. H of j omega is equal to minus infinity plus infinity h of t e power minus j omega t. It is simple Fourier transform. Then similarly, h of t is 1 by 2 pi integral minus infinity to plus infinity h of j omega e power j omega t omega. Ideal filter transfer function. So you can have this h of j omega value could be equal to e power minus j omega t naught. So omega mod omega less than or equal to omega c, and its value is 0 elsewhere. This is the low pass filter characteristics. Now substitute this value here. H of t is equal to 1 by 2 pi integral minus omega c to omega c e power minus j omega t naught e power j omega t d omega. Now if you try to simplify this, 1 by 2 pi integral minus omega c to c e power j omega t minus 3 omega. This is equal to 1 by 2 j t minus j omega t minus what? Evaluated at minus omega c and omega c by 2 pi j into t minus t naught j omega c t minus t naught minus e power minus j omega. Substituting this lower limit and upper limit in the above equation. This is equal to 1 by pi into t minus t naught and e power j omega c t minus t naught minus e power minus j omega c t naught. So taking this to the inside. Now this can be written as by pi t minus t naught into this is sin omega c t minus t naught. Now this is equal to omega c by pi. This can be written as sin omega c t minus omega c t minus t naught. This is equal to omega by pi and same function omega t naught. This is same function. So if you plot this same function, the peak value, this is the peak value centered in t naught. Maximum value will be omega c by pi. Main lobe width, this will be this 2 pi by this is 2 pi by omega c and this will be by omega c. From this we can understand that impulse response is also existed for t less than 0. Impulse response means at t equal to 0 we are applying impulse function. But before applying t we are getting some response. This is not practically realizable. Practically it is impossible to implement such a system, that is h of t equal to 0 for t then 0. This is for causal system. Therefore, it is clear that although ideal low-pass filter is very desirable, cannot realizable physically. In order to realize physically the low-pass filter, you need to go for polywiener criteria. Causality and polywiener criteria. Polywiener criteria gives the condition for causality in frequency domain. Causal physical realizability. The necessary and sufficient condition for magnitude function mod h of j omega integral minus infinity to plus infinity natural logarithm of mod h of j omega by 1 plus omega square and d omega should be less than infinity. And the above equation to be valid, then mod h of j omega must be be square integrable. Square in that is integral plus infinity to plus infinity mod h of j omega whole square d omega should be less than infinity. And this condition is known as wiener criteria. This condition is known as condition for causality and physical realizability. The Pauli-Wiener criteria gives the condition for physical realizability in frequency domain. Its time domain equivalent can be stated as follows. System which violates Pauli-Wiener criteria is anticipatory. Such a system produces response before excitation is applied. Such system is physically not realizable. The second condition is the system which satisfies the Pauli-Wiener criteria has causal unit sample response. That is, h of t impulse response must be equal to 0 for t less than 0. Interpretations of Pauli-Wiener criteria 1. So for a physically realizable system, mod h of j omega may be 0 at certain discrete frequencies, but it cannot be 0 over a finite band of frequencies, otherwise be infinite. And the second condition is for a physically realizable system, mod h of j omega cannot be decay faster than a function of exponential order. For example, h of j omega is equal to e power minus alpha into omega, represents realizable system. This is a realizable system. But h of e power j omega is equal to e alpha omega square, and this is not realizable system. Should have a it cannot decay faster. Coming to the bandwidth of a system, magnitude response has to be plotted. This is mod h of j omega, and we will find out at 3 dB points omega 1, and this is omega 2. Maximum is 0 dB, and this is minus 3 dB. It is the interval of frequencies over which the magnitude remains within 1 by root 2 times, that is minus 3 dB times in the midband. Difference between omega 2 minus omega 1 is defined as bandwidth. This is a system bandwidth. Coming to the signal bandwidth, so try to plot the signal spectrum. It is the range of significant signal frequencies which are present in the signal. Significant frequencies from omega 1 and omega 2, the bandwidth of the signal will be omega 2 minus omega 1. Transmission through the system will be distortionless if it has a infinite bandwidth. When the signal has infinite bandwidth, then the system bandwidth must be sufficiently high to accommodate the signal for distortion transmission. So we will have around 1%. This is about uh, signal bandwidth, omega 2 minus omega 1. The relation between rise time and bandwidth. This time, rise time TR is defined as the time required for the response to rise from percent to 90% of the final value. The rise time is inversely proportional to the bandwidth. Firstly, bandwidth into